Welcome back to Go Digital Essay Foundation's Ithala Education Platform Advanced Pillar. I'm your instructor Dave Semmelink from Go Digital Essay Foundation. Today we're doing Unit 10, Makerspaces, Part 2 of 2. So in the previous unit we looked at Makerspaces and 3D design and printing. In Unit 10 we will look at designing a 2D object and create it on a laser cutter. So what is a laser cutter? We know that a 3D printer builds a 3D object by laying down layers of 2D slices of a material, one layer at a time, until it has built the complete object. A laser cutter is used to cut shapes from a flat sheet of material, usually plastic, wood, or metal, but other materials are also possible. A machine called a pattern cutter can cut a 2D design out of cloth. A laser engraver uses a weaker laser to etch an image on the surface of the material. Laser cutters can cut much faster than 3D printers can print. They are generally more expensive than 3D printers. They can only cut and etch 2D designs. If you need to make a 3D object, you can design it from 2D parts that you then assemble. Okay, so these are some typical objects made in a laser cutter. This is a 3D object made out of 2D parts that are then assembled. Okay, we'll be using Openscad again. We used it before to make a 3D design, so this time we'll be making 2D designs. And the 2D design simply is something that is flat, like these panels. Okay, so we'll look at Openscad 2D commands. The first one is square. This creates a square or rectangle in the first quadrant. When center is true, the square is centered on the origin. The argument names are optional if given in the order shown here. So we can say square size equals, and the vector x and y, and the center is true or false. We can say square size equals x. In this case it's an actual square with both x and y being the same, and again center is true or false. So size is a single value, square with both sides this length, or two value vector x and y gives you a rectangle with dimensions x and y. Center can be false, which is the default, which means that the square is drawn in the first positive quadrant at one corner at the origin 0, 0, or center can be true, in which case the square is centered at the origin 0, 0. So default values, square without anything, it yields the same as square with a size of 1 and 1, and the center is false. So equivalent scripts for this, we can say square size equals 10, or square 10, or square 10 comma 10. These are all the same. Square 10 comma false, 10 comma 10 comma false, or center equals false, or size equals 10 comma 10, center equals false, or center equals false, size equals 10 comma 10. Okay, so notice that if you specify the name of the parameter, you can put them in any order. If you don't specify the name, then they have to be size and then center. And as you can see, that's drawing a square in the first quadrant with one corner at the origin. Okay, circle. This creates a circle at the origin. All parameters except r must be named. Okay, so it's circle, r equals the radius, or you can say d equals the diameter. So you can specify either the radius or the diameter. So parameters, r is the circle radius. R name is the only one optional with circle. Okay, so if you just say circle with a number, that is then assumed to be the radius. Okay, the circle resolution is based on size using $FA or $FS. We saw these before. We're going to talk about them again in a moment. but those are to improve the resolution of circles. So for a small high resolution circle, you can make a large circle, then scale it down, or you can set Fn or other special variables. Note that these examples exceed the resolution of a 3D printer as well as of the display screen. Okay, so we can scale a circle to create a higher resolution version of it, or we simply specify $Fn equals and then a fairly high number. Okay, d, circle diameter. Okay, so you can specify the diameter instead of the radius. Okay, so we saw $Fa and $Fs in the last unit. $Fa is the minimum angle in degrees of each fragment of the circle. So if you specify 360, that means that there will be 360 degrees in the circle, so 360 sides to the circle, so that will make a very smooth circle. If you specify a small number, let's say 2 or 3, then it will have very few segments or very few fragments of the circle, and so the circle will be very rough. Okay, you can use $Fs, which is the minimum circumferential length of each fragment, and $Fn is a fixed number of fragments in 360 degrees. So values of 3 or more override $Fa and $Fs. Okay, and these parameters must be named. Okay, so for defaults, if you just specify circle with no parameters, then it's the same of saying $Fn equals 0, $Fa equals 12, $Fs equals 2, and radius is 1. Okay, but normally you're going to specify the parameters that you need. Okay, again, so equivalent scripts, circle 10 is the same thing as saying circle r equals 10. It's the same as saying circle d equals 20, because the diameter is double the radius. And it's the same as saying circle d equals 2 plus 9 times 2. Okay, basically that works out to 20. So that means that you can do calculations, obviously, in your parameters. Okay, and that gives you a circle. In this case, it's centered at the origin. Ellipse. An ellipse can be created from a circle by using either scale or resize to make the x and y dimensions unequal. Okay, so there's no ellipse command. You have to use the circle command. And what you do is you say resize. So that's a transformational command that says we want to change the size of this circle by 30 in the x direction and 10 in the y direction. Since they're different, it's going to make an ellipse instead of a circle. And likewise, you could say scale, which is another transformational command. You say scale 1.5 comma 0.5. Okay, then it's going to be 1.5 times the size in the x direction and 0.5 in the y direction. Okay, and it should be obvious that resize and scale can be applied to other shapes. We're just doing it here for circle to show that you can turn a circle into an ellipse. Polygon creates a multiple-sided shape from a list of xy coordinates. A polygon is the most powerful 2D object. It can create anything that circle and squares can, as well as much more. This includes irregular shapes with both concave and convex edges. In addition, it can place holes within that shape. So the polygon statement is polygon, and then parameters are points equal, and a list of points. And the list of points is a list of vectors. So it's xy pairs, and there's a list of those. And it can have paths, and it can have convexity. So parameters, the list of xy points of the polygon. That's a vector of 2 element vectors. So note, points are indexed from 0 to n minus 1. Okay, as we've seen, we always start our lists at 0. Paths, if no path is specified, all points are used in the order listed. Single vector, the order to traverse points, uses indices from 0 to n-1, may be in a different order, and use all or part of the points listed. And multiple vectors creates primary and secondary shapes. Secondary shapes are subtracted from the primary shape, like difference. Secondary shapes may be wholly or partially within the primary shape. A closed shape is created by returning from the last point specified to the first. So example with no holes. Okay, so if you got polygon and points equals, and now we've got a list of vectors. So the first point, let's say, is 0, 0, so that starts here. The next point is 100, 0, so it's at 100 millimeters with y equals 0. The next one is 130, 50. So x is 130 and y is 50. And the next one is 30, 50. So x is now 30 and y is still 50. Okay, so that creates this polygon. Okay, if you specify paths, you can change the order of the points in the list. So this next one, it's got the same order as the previous one, and paths is set equal to 0, 1, 2, 3. So it shows that the order is the same. So in this example, the paths are reversed, 3, 2, 1, 0. So these are in the same order as before, but now it's going to start at the fourth one, whose index is 3. So it starts here, then goes there, then goes there, then goes there. And likewise with the last one, we're just doing it in a random order. So we're taking index 1, then index 0, then index 3, then index 2. Okay, but these all give you the same shape. Okay, and here we're using variables. In Openscad, you create a variable by giving it a name and setting it equal to something. So here we're making a equal to this set of vectors, and we're making b equal to that set of vectors. So we can say polygon A. So A is our set of points. Polygon A comma B, or B is now our path. And we can also mix it so we can have polygon A and then specify the path. Okay, example with one hole. So here we've got polygon with points 0, 0, 100, 0, 0, 100, 10, 10, 80, 10, 10, 80. Paths is 0, 1, 2, then 3, 4, 5. And we're setting convexity to 10. We're setting this variable triangle points equal to this set of vectors, and setting triangle paths to this set of vectors. And then we've got our polygon, triangle points, triangle paths with convexity 10. So the first path vector, 0, 1, 2, selects the points 0, 0, 100, 0, 0, 100 for the primary shape. The second path vector, 3, 4, 5, selects the points 10, 10, 80, 10, 10, 80 for the secondary shape. The secondary shape is subtracted from the primary. Okay, we're taking the difference. Since the secondary is wholly within the primary, it leaves a shape with a hole. Okay, let's think about that for a moment. We've created a big triangle using polygon, and now we create a smaller triangle over here. So if you imagine something that's cutting a flat sheet, when it cuts like this, it makes a big triangle. When it cuts like that, it will cut this triangle out of the big triangle. So we end up with a shape with a hole in it. And we just have an example here with multiple holes. Okay, so we've got a polygon with A, B. A combines all of these. So A0 is this set of vectors. That's our main shape. And B0 is our path. A1 is in this set of vectors. B is the paths. B1 is paths. A2 is this set of vectors, which hold 2. B is that set of paths. And so on. A3 like that, B3 like that, A4 like that, B4 like that. So A, we've put together, using concat, we concatenate those vectors. So A0, A1, A2, A3, and A4 are combined. And the paths are combined in this vector. So now when we say polygon A, comma B, we're putting all of these together, which will give us this shape with those shapes cut out of it. And this, of course, is the same as this, where we've got polygon A is again the same, and B, instead of using B, we've just specified it. So this is the same as that. Okay, text. The text module creates text as a 2D geometric object using fonts installed on the local system or provided as separate font file. The parameters for text is a string, that's the text to generate. The size, so this is a decimal number, it's the generated text, has an ascent, height above the baseline of approximately the given value. Default is 10, okay, so that's roughly 10 millimeters. Different fonts can vary somewhat and may not fill the size specified exactly. Typically, they render slightly smaller. Okay, you might notice it if you're looking at any text. Some text takes up less space than others. Let's just look at the word height. H and E are about the same width, but I is much narrower than those two. T is also narrower than G or H. So different letters take up different amounts of space. And then font, this is a string. It's the name of the font that should be used. This is not the name of the font file, but the logical font name, which is internally handled by the font config library. This can also include a style parameter, which we'll see just now. A list of installed fonts and styles can be obtained by using the list dialog. Okay, if you select the help menu, there's an option font list. If you click on that, then it will list all the fonts supported by the local computer. Okay, other parameters are halign. Okay, that's a string, and that's the horizontal alignment for the text. The values are left, center, and right, with the default being left. valign, that's a string, and the vertical alignment for the text. Possible values are top, center, and baseline, and bottom, and the default is baseline. Spacing, that's a decimal value. It's a factor to increase or decrease the character spacing. The default value of 1 results in the normal spacing for the font. Giving a value greater than 1 causes the letters to be spaced further apart. The direction, that's a string. It's the direction of the text flow. Possible values are left to right, or LTR, RTL for right to left, TTB for top to bottom, and BTT for bottom to top. And the default is left to right, LTR. Language, it's a string, the language of the text. The default is EN. Okay, EN is the common abbreviation for English. So you can specify other languages. Script, that's the script of the text. The default is Latin. And $FN is used for subdividing the curved path segments provided by FreeType. Okay, these all have defaults. We're typically going to leave this at the default. We'll typically leave script at the default. We'll normally leave language as the default unless we want to specify a different language. Normally it's going to be LTR. It would be RTL for certain languages, and top to bottom for certain languages, but normally it's left to right. Spacing we normally leave alone. So it's just horizontal alignment, vertical alignment that we might sometimes change. Okay, so as an example, if we have text in Openscad, then it will simply render Openscad. Okay, to allow specification of particular Unicode characters, you can specify them in a string with the following escape codes. Okay, we don't have to worry about this too much. I don't know if you know about it, but we can specify different character sets or different character codes using Unicode. If you do \x and then a 2-digit number, and that's a hexadecimal number from 01 to 7F, you can specify any ASCII character. If you do \u and then 4-digit number, those are Unicode characters with 4 hexadecimal digits. And \U with 6 hexadecimal digits, then that's a Unicode character with 6 hexadecimal digits. And you can do null character as well. Okay, these are things you don't normally have to worry about, but you can do some special characters that are useful. Okay, here's an example where we've got the euro symbol and a smiley. So the euro character is \U20AC, and now that's followed by 10. So it's going to do the euro symbol and then 10. So you see euro symbol and then 10. And then there's a space, and then \U263A. That gives us a smiley face. Okay, so using fonts and styles. Fonts are specified by their logical font name. In addition, a style parameter can be added to select a specific font style like bold or italic. Okay, such as font is Liberation Sans. Okay, that's the name of a font. And then we can have a colon and say style equals bold to make it bold. And we can say italic, so it's going to be italic. So if we say style equals bold space italic, then it's going to be both bold and italic. The font list dialog, which we find under Help Font List, shows the font name and the font style for each available font. For reference, the dialog also displays the location of the font file. You can drag a font in the font list into the editor window to use in the text statement. So you can add fonts to it if you like. Openscad includes the fonts Liberation Mono, Liberation Sans, and Liberation Serif. Hence, as fonts in general differ by platform type, use of these included fonts is likely to be portable across platforms. For common casual text usage, the specification of one of these fonts is recommended for this reason. Liberation Sans is the default font to encourage this. This is an interesting thing about Windows PCs. Different PCs could have different fonts installed. So if you use a fancy font on your PC, and now you try to print it on somebody else's PC, you might find out that font doesn't exist. So if you just need basic font, they recommend using one of the built-in included fonts, because those are always guaranteed to be the same on any computer. In addition to the installed fonts, it's possible to add project-specific font files. Supported font files formats are TrueType fonts, those that end with .ttf, and OpenType fonts, those that end with .otf. The files need to be registered with use. Okay, so if you want to use a funny font, then you say use and in these brackets, so less than sign, ttf/paratype serif, like that, and that's the name of the file, and close the brackets with a greater than sign. That registers the font with Openscad, and then the font is listed in the font list dialog, so in case logical name of a font is unknown, it can be looked up as it was registered. Okay, so here's some examples. You can say square 10, translate 1515, text Openscad font liberation sans. Okay, so square 10 makes a square, starting at the origin here. Translate 1515, that's shifting it 15 over and 15 up, and then text Openscad, so it's going to create Openscad and using the font liberation sans. Then we got translate 15:0. Okay, so that moves it across 15 and up 0, so in other words it's on the same line. We're using font liberation sans. The style is bold italic, so this you can see is bold italic. Okay, alignment, vertical alignment. Okay, so if we specify v-align top, the text is aligned with the top of the bounding box at the given y coordinate. Okay, so here it's aligned at the top. Center, the text is aligned with the center of the bounding box at the given y coordinate. So here it's centered on the line. Baseline, the text is aligned with the font baseline at the given y coordinate. Again, this is the default. So here it's aligned at the bottom, but you'll see letters like G, lowercase g, where it goes below the line. And finally, bottom, the text is aligned with the bottom of the bounding box at the given y coordinate. So here we can see even the G has been shifted so that it's on the bottom line. Okay, so the default is baseline, and this is usually the best one to go with. Okay, then horizontal alignment. So if we specify left, the text is aligned with the left side of the bounding box, and this is the default. That's this one. Center, the text is aligned with the center of the bounding box, so that's in the center. And right, the text is aligned with the right of the bounding box. Okay, so that's on the right. So the default is lining it on the left side. Okay, so those are the basics of 2D commands in Openscad. So now let's design something. So let's design an object that we can create on the laser cutter. We will start with a simple 2D object, a keyring tag. It can be as simple as a rectangle with a hole for a ring to go through. We will make it 16 millimeters wide and 5 times 16 millimeters long. And we'll make a 3 millimeter hole at one end. Note the hole is in the wrong place in our example here. So here we say square, and x is 5 times 16, y is 16. So it goes across 5 times 16 and goes up by 16. And then we want a hole for a ring to go through, so we say circle with a radius of 3 divided by 2. So the diameter is going to be 3. Okay, but this hole is in the wrong place. We need to shift the hole or the rectangle so that the hole is in the right place. So we move the rectangle half its width down and half its width to the left. Now we know the hole is in the right place, but we can't see it. Okay, we're saying translate -8 minus 8, so it goes back by 8 and down by 8 before we draw the rectangle. And then our circle's in the same place, so now the hole is here. Okay, the problem is we can't see the hole. So we give colors to the objects. We'll make the rectangle green and the hole black. Note that these are just the colors that appear in Openscad. The laser cutter is simply cutting a sheet of plastic, so the colors don't affect the color of the object. But we will see just now that there is another reason for assigning colors to the shapes. Okay, so if we say color green before we say translate and square, then it will make this rectangle green. If we say color black before we do the circle, then it makes the circle black. Okay, our program works, but we need to do it properly. So first let's add some comments. We should always start with a comment block giving the name of the file, the name of the author, the date it was created, each date when it is modified, and a description of what it does. So we always start our Openscad programs with a comment block. So we give the name of the file, so it's // to show that this is a comment. This is the name of the file, it's 2D nametags.scad. Then the author, name of the person creating the program, the date it's created, and if we go back and modify the file later, we can add the date that it's modified. So we keep the creation date, and then we can add modified date. Then we have to say what the file does. So we say it's a 2D file for laser cut keyring tags. Then we've got color green, translate, square, and color black, circle. Next, we want the program to be flexible. Instead of specifying each dimension, we should use variables at the top of the program so we can change the size of the tags easily. In Openscad, you declare variables by giving each a name and assigning them a value. Okay, so we've got y1 is 16, that's the height of this tag. x1, we're saying that's 5 times y1. Okay, by doing it this way, then if later we decide we want y1 to be 20, then we just leave x1 at 5 times y1 because that's now 5 times 20. Okay, so that's the height of the tag. That's the length of the tag. M3 is 3 divided by 2. That's the whole diameter. Okay, it's 3 millimeters. M3 is the radius. So if the diameter is 3, then we have to divide by 2 to get the radius. Okay, so now we say color green, translate, and we're moving it by negative y1 divided by 2 on the x-axis. So this was 16, so we want to move it by 8, and it's negative. So we're moving it, shifting it over negative 8. And then the y value, again, it's y1 divided by 2, so we're shifting it down by 8. Okay, and that's square x1, y1. Okay, and the circle is after that. Okay, and notice now that if we want, like I said before, if we want to change y1 to 20, we just change it to 20 here. That will change the height. It will also change the length. And it changes how much it shifts it by. So they always work out the same. So one other variable here, we've got $FN equals 32, but you see that I've commented it out. So we uncomment this when we render to make it smooth. Okay, so by saying $FN equals 32, it makes the circle smooth, but it will also take it much longer to preview. So we comment this out until we're finished with the file, and once we're happy with everything, then we remove the comment, and then we render it, and now it will have nice smooth circles. And just note that when you're working with 2D objects, when you want to preview, you press F5, and you'll see all the different objects, including the circle. But when you press F6 to render it, it shows where it's going to cut on the outside. It doesn't show where it's cutting the circle. I don't know if this is a bug or that's just how it works, but you won't see it. But you don't worry about it. Pressing F5, you'll see the circle. Pressing F6 will render it to make it ready to print. Okay, if we're happy with this, next we need to export a file that the laser cutter can use. Unlike 3D printers, laser cutters need a 2D design file. Okay, so we will export to the DFX format. This is a very popular format for laser cutters. Remember that when we were making 3D objects for the 3D printer, we exported as an STL file, and we could use F7 instead. But for 2D, we export as a Dxf file. So we always use the export menu, go down to export as DXF. If we look in the folder, we now have two files, the SCAD file that we are working on and the Dxf file that was exported. If we take the Dxf file to the laser cutter, we can create the tag. Okay, so you'll see we've got two files. The file we're creating, 2dnametag.scad, is our Openscad file, and then 2dnametag.dxf is the Dxf file that we would take to the laser cutter. Okay, now if we're making a key tag, we might want to put people's names on it. We use the Openscad text command to create the text. Apart from specifying the text to print, we can set the font size, font name, horizontal alignment, and vertical alignment. Okay, so I've made it red so that we can see it. Say translate. Okay, so in this case, because we moved the rectangle over by half of the height in the left direction, we'll start the text with half of the height in the right direction. Okay, there's no minus sign here. So we shifted the rectangle over here, and we want to start the text over here. Okay, and then we got the text, which is just Dave. So it shows Dave here. Said the size is 12. The font is Courier New, which is a very common font. Horizontal alignment is left, so it lines up on the left. Vertical alignment is baseline, so the bottom lines up here. Okay, the -5 I got with a little bit of experimentation. I had used half of 12, that made it -6, but then that got a little bit too close to the bottom. It wasn't nicely centered. So I found out that by using -5, it centered it nicely this way. Okay, since we might want to change the font name and size, we should use variables for these. Okay, so instead of specifying the font name and the font size, we create a variable font size, and we set it to the size that we want. In this case, we're making the font 3/4 the height of the tag. So we say the font size is 3/4 times y1. And again, that means that if later we decide to make the tags bigger and change y1 to 20, the font size will now be 3/4 of 20. So the font will be bigger, but it will still be 3/4 the size of the height. And I've set the font name to Courier New. If I decide to change that later, I only have to change it here. I don't have to change it inside the program. Another programming concept we can take advantage of is modules. These are called functions or subroutines in other computer languages. The idea is that if we have some code that is useful and that we might make use of again, we put it in a module so we can simply call the module. To make a module, you start with the module keyword, then give the module a name, for example, make tag, followed by parentheses. Okay, so you can see here, I say module. I've given the name of the module. I've made it make tag. Then I've got parentheses, and I've got a parameter, which is name. Okay, so we put parameters inside the parentheses. Since the module is going to print a name on the tag, we just call it name. We put the code for making the tag in between the curly braces. So after saying module, the name of the module, make tag, and the parameters inside parentheses, we now start with an opening curly brace, and that start has to have a closing curly brace, and then whatever code we want to run inside, we put between the two curly braces. So now if I want to run this module, I just say make tag and Dave, and this will run this module. Okay, while we're at it, notice that the length of 5 times the height might not be long enough for long names. To handle different size names, we can use the number of characters in the name to determine the length of the tag. The function leng returns the length, that is the number of characters in the name. So we make the length of the rectangle n times y1. Okay, so when we call our module, it's past the name. We're going to set variable n equals to leng name. So that's the number of characters in name. The rectangle then is going to be n times y1. So the length of the name times the height. This means that if your name is 4 characters long, it's going to make it 4 times the height. If the name is 10 characters long, it's going to make it 10 times the height, so it will be longer. Okay, and just note that we don't need that x1 variable anymore, so we can remove it. Okay, I've removed x1. We had the x1 up here being 5 times y1, but now, because we've specified the name as being n times y1, we don't need x1 anymore. Okay, let's make it more flexible again. Let's say we wanted to print several tags for different people. For 2 people, we can simply repeat the call to the module. But remember that we need to move the next tag away from the first tag, so we need to add a translate. We know the tags are y1 high, and we'd like to leave some space between them, so we add another 5 millimeters. Okay, so I haven't changed anything here. I've said make tag Dave, and below it I've got make tag Sabani, but I wanted to print this tag above the first tag. So I say translate 0 for x, so it doesn't move this way, and then y1 plus 5. So y1 is the height of the tag, and then plus 5 is another 5 millimeters. So it makes the second tag above the first one. If we want to do 3 tags, we can carry on like this. Okay, so now I want 3 tags. So I've done another one, and I've had to move it up. The first one was up y1 plus 5. So the third one has to be 2 times y1 plus 5. Okay, so now we've made our tag Ntabisang. So we've shifted the first one up by y1 plus 5. And we've shifted this one up by 2 times y1 plus 5. Okay, but you already know from making applications in Make Code that there's a better way to repeat code. We can use a loop. In this case, a for loop will work well. But before we make the loop, how do we specify a list of names? Okay, in Openscad, we make a list using square brackets. So our 3 names are put in a list named names. Okay, so we create a variable names, and it's equal to this list of strings. So in square brackets, we've got Dave, comma, Sabani, comma, Ntabisang. Okay, close the brackets and then semicolon. So names is now equal to this list of 3 names. Now we can use a for loop to call make tag for each name. The for loop has a counter variable I that starts at 0 and ends at the number of names in the list, less 1, because list counters always start at 0, not at 1. Okay, so we've got a for loop. Our for loop starts with 4, and then inside parentheses, we specify the start and end values for I. So we say I equals this, it's going to start at 0, and it's going to end at leng names minus 1. Leng names, okay, that's the number of items in the list, is going to be 3. Okay, there's 3 items in this list, so leng names is 3. We want I to start at 0, which is going to be our first item. It then has to go to 1, which is the second item, and then it has to end on 2, which is the third item. So it has to end at 2. which is length names minus 1. Okay, so then we open up our curly braces, and in here is what's going to be repeated, and then we close the curly braces. We also need to translate by different amounts for each tag. We were manually calculating this before, but now we simply make it I times y1 plus 5. So you'll see that when the first time through the loop, I is 0, so I times y1 plus 5 is 0. So that means the first tag isn't moved up. Second time through the loop, I is equal to 1. So it's 1 times y1 plus 5. So it shifts it up by y1 plus 5. The third time through the loop, I is equal to 2. So it's 2 times y1 plus 5. So it shifts it up by y1 plus 5, y1 plus 5 up here. So now when the list of names changes, the only change we need to make is to the list. Okay, so now we want to do some more tags. So just give it the list of names we want to make. Everything else stays the same. Okay, so in this case, we've got a list of 1, 2, 3, 4, 5, 6, 7, 8, 9 names. So it will print them like that. Okay, we're almost done. We can now uncomment the line with the $FN equals 32 so that the holes will be smooth. Okay, so I've removed the double slash here. So next we press F6 to render the design. Okay, it will look a little bit different, but don't worry about that. Okay, so it will look like this. Okay, you don't see the names, you don't see the holes, but don't worry about it. When you render, it's developing it so that it's ready to be exported. Finally, we need to make the file for the laser cutter. From the file menu, we select export, then export as DFX. Okay, that will create the DFX file, which you'll then take to the laser cutter and you load it into its control program. One thing we didn't mention is how does the laser cutter know that it needs to cut the tags and the hole for the ring, but it has to engrave or etch the names. To do this, after loading the file on the laser cutter, we tell it that red color is for etching and the green and black colors are for cutting. The laser cuts at full power and etches at reduced power. Let's now watch the laser cutter making our tags. Note that the video is of us printing a lot of tags, so we also did several rows of them. Before we finish, I just want to show you how we can make a 3D object using 2D parts. So I've designed a cabinet. This is actually going to be an intercom, or a case for an intercom. So you can see it's got two sides. It's got a bottom, it's got a top, it's got a back. The back has holes in it so that we can mount it. And then there's tabs along all the edges so that the parts can fit together. There's also a hole in the bottom. for a wire to go through. You can see the hole there. Okay, so how do we make this? Well, we just have to design each of the parts. The parts consist of the top, the bottom, the side, and it's got two sides that are identical, so we'll make two of those, and the back. And this is how the parts look when they're laid out flat. And this is how they will be cut on the laser cutter. So basically, let's just take a look at the side. So I've created a module called case side. And it's basically polygon of points where we've got thickness, that's the thickness of the plastic sheet, which is 3 millimeters. Then we've got the case depth, and you saw that the bottom of the case is not as deep as the top of the case. So I've got case depth bottom, which is 60 millimeters. Case depth top, which is 120 millimeters. So the top is double the size of the bottom. The case height is 150, so it's 150 from the top to the bottom. Then the case width is 106 wide. Okay, so the back, the top, and the bottom will all be 106, so they'll all use case width as their width. And then the sides and the back will have the case height. And as we saw, the case depth for the bottom and the top. Okay, so basically it's just a matter of creating polygons. And then I've used squares to make the little tabs along the edges. So that's the side. The top. Again, that's a square with the tabs along the sides. The bottom. Okay, that's the bottom. Again, a square with the tabs on the sides. And then it's also got a circle to make a hole for the wires. Okay, and the case back. Okay, so basically all we've done is we've created modules to create each of these, and then to lay them out like this, we start with the case side, and we translate it by 0 along the x-axis. The second side, it's the same module, case side, but now I wanted them close to each other so we don't waste any of the plastic sheet that we're cutting this out of. So I've turned it around so the two will fit together nicely. Then we've got the case back. Again, we've shifted it over along the x-axis. Case top, we shift it over again. And the case bottom, shift it over to the side. Okay, so this gives us the layout for all of our parts. We then press F6 to render it. Next, we export the file. Go to the File menu, Export, and we want to export it as a Dxf file. It'll prompt you for the name, but it uses the same name as the SCAD file, but with .dxf. We can say save. And that then is the file that we take to the laser cutter. Okay, and it will work exactly the same as it did for the keychain tags. The laser cutter will simply cut these out of a big sheet of plastic. And when they're cut, all we have to do is to glue them together. So what next? This has been an introduction to designing 2D objects and creating them on a laser cutter. We have covered these topics in the series, from Unit 1, Digital Literacy, right through to Makerspaces and laser cutting. This is the end of the Digital Literacy Advanced platform. I hope you have learned a lot from the series and would like to learn more. We will be doing more of these programs in future, so I hope to see you then.